Hello, thank you for watching this pre-recorded presentation. The bottom picture is the skyline of Shanghai. We are in Fudan University in the city of Shanghai. Thanks for the meeting organizer to give me the chance to present our work from the past 6 years. I'm Liang and my email is at the bottom of the page. It is a group effort. Different instructors contribute their expertise in various fields in biology and build a total of 6 learning modules for freshmen to choose in one courses that I'm going to introduce in this video. Justin Fendos was a HHMI teaching fellow. He helped us design the critical components of the course. Research confidence and competence are key to science training, and effect training has generally occurred through traditional undergraduate research experience, during which tensions do exist. A sizable body of work has studied the challenges associated with such training in West settings. Here, I'll start the video with our 2014 survey result, listing the training challenges exist in Asian settings. Then I'll briefly list the SoTL methods we used during the course reform. Next, I'll introduce one course and how it iterated over the past 5 years, and its current structure, and most importantly, the reform outcomes. We are in the process reconstructing more courses following the first success to improve students' learning experience and to enhance the sense of achievements for mentors. Back in 2014, we interviewed faculties and postgraduates who usually oversee day-to-day activities of newbies joining a lab, as well as undergrads in the School of Life Sciences. 8 challenges were identified. The first challenger was mentioned most often by undergrads. As one student put it, find a lab I think is already one of the hardest parts. Even though it is a graduation requirement, there is no list of labs we can look at to know which professors might want an undergrad. The second challenge again was mentioned most often by undergrads, who expressed concerns about not knowing what qualifications were needed before joining a lab. One student said, I actually want to work in a lab after my first year, but I was worried my lab skill won't good enough to do a good job and make a good impression. So I waited a long time before joining a lab in my third year. The third challenge was a low starting research competence, mentioned most by faculties and postgraduates. Undergrads generally agree with this issue, as one saying, I had already taken 8 lab courses, but I found those experiences did not really transfer to my thesis work. I feel most lab courses focus too much on getting the right answer, which already predetermined. What we need is the chance to think about and consider the unknown, which is more what we do in a real research lab. While the first 2 challenges are about how to join a lab, the rest 6 challenges exist after joining a lab. For the third challenge from the interviews, clearly, due to the typical lab courses were generally cookbook in nature, there is a great potential to implant course-based research experience to teach students with basic lab skills. Challenge 4 and 8 mentioned most by postgraduates. Undergrads were also aware of those tensions. One said, I often worry I'm annoying my mentors and wasting their time. Challenge 5 strongly suggests that shifting the burden of expensive material cost away from the head of the lab might be useful for reducing in-lab tension. The sixth challenge was primarily raised by faculties. Some do find some undergrads very engaged in their work and had meaningful contributions to the research project. They also find classes and exams can be very disruptive to research productivity, which motivate us to design a course in summer rather than mid-semester. For the seventh challenge, undergrads know there are several negative consequences to join a lab late, and faculties view it as a factor that affects research productivity. We, as the course designers, see an intervention might have greatest impact by targeting second-year students, better preparing them for early starts in research labs. So far, I have listed 8 challenges exist in our university using focus groups and interviews. Next, we design courses to address these 8 challenges. For each course, we design enter and exit surveys to collect self-assessed learning gains. Also, we formulate learning activity-specific rubrics to collect data on improvements during the course. To further document the differences, as X courses and non-courses students progress through their undergraduate careers, we conduct a series of follow-up surveys. In addition to these surveys, focus groups and interviews were implemented to collect detailed information about their experience in research labs, with undergraduates as well as faculty and postgraduates. In order to address these eight challenges, in summary, we build the following features into the course we reform. Incorporating 6 diverse topics into one course was motivated by the desire to give the learners a greater opportunity to explore their interests, and all the faculties actively looking for undergrads were invited to participate, so undergrads would have the opportunity to interact with prospective mentors within the course. Within the courses, we emphasize on basic lab skills commonly used in all research labs, emphasize on transferable skills to prepare students to join their first lab after course, also motivate them to have an early start. We repeatedly ask students to write proposals and reports. Both are essential real lab experience. Most lab research was conducted cooperatively. We built this feature in the course with the hope to help peer-to-peer influence. We deploy evidence-based teaching in all learning activities. In lab, students' performance was carefully monitored using rubrics, with each rubric being used at least twice to give pre-learning and post-learning assessments. Most teaching assistants were postgraduates, newly recruited to the courses. They all required to participate in a 2-week-long instructor training. The first week focused on introducing a foundation of active learning and scientific teaching, and the second week focused on building their own activity modules and familiarize with the module they are going to teach and made adjustments if needed. Our course built with those features was very successful. Here is a table showing the data that one course has addressed both challenges 1 and 2. For students enrolled in the university in the fall of 2014, they might participate in the course in the summer of 2015. Before that, there was no reformed course. Significantly, students participate in the course more than twice are likely to have multiple research lab experience in their second year and also in their third or higher years. As one student in the follow-up focus group said, because I did not participate in the course, I think it's easy for me to notice the difference. The students participate in the course also much more like to talk about research. Sometimes they were among themselves to talk about their different lab projects, and that can be annoying sometimes. So far, I have listed the challenges and the course features implemented during the reform, and I give one outcome of the course, but I have not introduced the course to you. The course run in the summer, avoiding the mid-semester burden to the student. It is also good for us to analyze the teaching outcome. It is the only class students took months. It composed of 3 parts. The first 3 days are basic training on basic lab techniques such as PCR, stereo operation, etc. Then the students will attempt 2 modules according to their interest. Each module lasts 15 days. Please note that fly and mouse genetic only run once, while other 4 modules run twice. Learning activity in the module are authentic, which means the students own their experiments and they improve their experiments based on initial results. Being authentic is very different from traditional cookbook-style lab courses. We want students to have a learning experience just like working in a real research lab. Here's an example. For a student, he attempts the basic training, then cell biology as his first module and fish genetics as his second module. There are different learning activities. Students have to do experiments, to discuss and write a proposal before performing the experiments, to write reports after experiments. All these are ways to make learning activity authentic, since both planning and organizing and interpreting data are universal parts of scientific process. Here's a timeline. For undergrads, they apply to participate in the course in May and attend the course in July. newly recruited postgraduates will be teaching assistant for the course, and the TA training happens in late May and June. As instructors, when we first started at the end of 2014, there was a lot of work. Then we made adjustments after running the courses. Since 2017, most of the learning activities are settled. They are not much changed. Our emphasis was the TA training because most TA change every year. While the course grounded on science training challenges in our university and with one goal to empower students with skill to start their research early, it is important to pay attention to other parties in the learning. Seeing students improve over iterations within the course immediately give instructor a sense of success. What is more rewarding is after the course, undergrads join the instructor's lab and later became his graduate students. We see there's an opportunity to build a learning community through courses, for undergrads to get better training, for postgraduates to get motivation, and for faculty to get inspiration. There's one feature that I would like to emphasize again. We focus on students' skill development rather than knowledge transfer. In the graph, the skill was assessed by rubric 2. The rubric is about proposal writing, including three sections: hypothesis, prediction, and procedures. There are three repeats, so three assessments shown as T0, T1, T2. The y-axis is the percentage of students getting the 4 points for each rubric item. As shown by the green arrow, items 7-1, 7-2, and 7-3 increased with repeats. What are these? Let's look at the rubric. 7-1 is about text required in the figure legend. 7-2 is about numbers in the figure legend. 7-3 is about how much experimental details should be included in the figure legends. This graph shows that students' skill in writing a proposal improves with repeats. We give the rubric to the students prior to the assessment. Teaching assistant give one-to-one feedback to students after they submit their first version, the second, and the third. Clear and detailed rubric could guide the students on learning to help them to form clear learning expectations. Now another example. Most the items got the 4 points even in T0, except 4-1. Let's look at the rubric. Item 4-1 is about self-plating, which of course improves over practice. These two examples demonstrate the development of skills during the course to help students grow their own research competence is the way to empower students. Perhaps the most important limitation of our study is the learner recruitment process. Due to its voluntary nature, our study may bias in favor of students already had a great interest in research. At current stage, there is nothing we can do about it. One interesting observation we had after analyzing the interview is that students develop some negative feelings towards science. It is based on word choice. Here is a year-to-year change, and let's just look at the combined values. The course made the student understand the nature of science, being challenging and difficult. Many students affirm that such understanding was likely necessary to gain an accurate and realistic appreciation of research in a lab. Biology Intensive Orientation Summer BIOS is the course I introduced to you today. Besides BIOS, there are courses being reformed AIBS. In BIOS, we emphasize on research confidence and research competence. In later courses, students will further develop field-specific lab skills beyond the basic skills. Limited by the English skills of rising sophomores, we did not include literature reading in BIOS, which is introduced in later AIBS. In addition, posters and formal presentations are introduced in later AIBS as well, to give students a simple to complex science skill learning process during their entire undergraduate careers. Thank you for your attention, and here are the funding sources. Feel free to email me if you have any questions. Bye bye.